I'm going to talk about spring forces, spring potential energy, and pendulums. All right, so let me draw a picture of what's referred to as a mass spring system, and let's discuss the spring force on a certain object. So imagine that I had a box of mass M, and it was attached to one end of a spring, and the other end of the spring was attached to a vertical wall, and the mass was moving back and forth to the right and to the left. So it's a repetitive motion system. All right. Now, let me also define an x-axis with respect to the ground, and I want the origin of this x-axis, the 0, to be to correspond to the position that the mass would be at if it wasn't moving. Okay, so if the spring was not compressed or stretched. All right, so if I move the box to the position corresponding to x equal to 2, okay, what direction would the spring apply a force to the box in? So at the x equal to 2 position, can you see that the spring would be stretched, and the spring would want to pull the box to the left? So at the x equal to 2 position, the spring force would be in that direction. Okay. On the other hand, let's suppose that the box was at the x equal to -2 position. Can you see that in that situation the spring would be compressed and it would apply a force to the right? Okay. So in other words, at the x equal 2 position, the force is in this direction. So I'm drawing red arrows to correspond to the direction of forces at various positions. And of course, at the origin, there is no force. That's the length that at the origin, the spring is the length that it wants to be. Okay, so we've got a situation where when the x value is positive, the force is in the negative direction, the negative x direction. When the x value is negative, the force is in the positive x direction. Okay, so keep that in mind. One more thing now. How does the strength of the spring force change as x changes? For example, at x equal 2, I have a certain force to the left. Now, what if I moved the box to the position corresponding to x equal to 4? Would the force to the left be more, less, or the same? Okay, you can get an actual spring to test this, and my prediction is that as you stretch the spring more and more, it's going to want to resist more and more. Okay, likewise, if you compress the spring more and more, it's going to want to push back more and more. So not only is the force, the direction correspond to the opposite sign of the x value, but it also increases as the absolute value of x gets bigger. The magnitude of the strength of the force does. All right, so all of that is to argue for the following form for the spring force formula. Okay? So the force on a mass attached to a spring is equal to minus kx. All right? The reason for the minus is to remind us that it's always in the opposite direction, okay? In other words, if x is positive, it's in the negative x direction. If x is negative, it's in the positive x direction, all right? And the k is a constant that is different, or that corresponds to specific springs, okay? A really stiff spring will have a lot bigger force if you stretch it 1 centimeter compared to a less stiff spring, all right? So the K constant alters the magnitude, the strength of the force, all right? Now, as you stretch and compress a spring, you also add potential energy to a spring system. All right? Think about a dart gun. When you push a dart into a dart gun, you're compressing a spring, okay? That has the ability to do work. You can convert that, what's called spring potential energy, into kinetic energy. How do you do that? You pull the trigger, and then the spring expands, okay, goes back to its normal position, the position it wants to be, and then the dart comes flying out. All right? So all of that is to say that we can define a spring potential energy formula. And that is 1/2 kx squared. All right? The units of the spring force are newtons, like for all forces. The units of the spring potential energy for the spring potential energy formula are joules, just like for all work and energy. Okay? Now, let's do some examples using these two formulas. Now, let me quickly mention that the pendulum, a pendulum system has a net force and also a potential energy that's similar to the formulas for the pendulum force and pendulum potential energy are similar to the ones for the mass spring system. Okay, even though a pendulum doesn't actually have a spring, mathematically the formulas look like as if it was a mass spring system. Okay, I'll talk more about that in a different video, but just know that systems can behave as if they were a mass spring system even when they're not. All right, so let's do some examples. Okay, so suppose I had a spring that had the K value. By the way, K is called the spring constant. So let's say that the spring constant, the K value, is 5 newtons per meter. Okay, and let's say that I had a mass on the edge of the spring, and I moved it away from the position that it would be if the spring wasn't applying a force. By the way, the position that the spring wants the object attached to it to be at, that's called the equilibrium position. Okay, so x equal to 0, you'll see it's sometimes referred to for a mass spring system as the equilibrium position. All right, so let's say the object was 0.1 meters from the equilibrium position. In other words, from the origin. Okay, so what is the force that the spring is applying to the object, and what is the corresponding spring potential energy? Okay, well, to calculate that, we would calculate minus kx, okay, and so that would give us minus 5 times 0.1, or minus 0.5 newtons. All right, so that tells us that if positive x values are to the right of the origin, that the force is to the left. Okay, now if you wanted to know the strength of the force, what's referred to as the magnitude of the force, that's the absolute value. So you would state that as 0.5 newtons. Okay, and drop the negative sign. And now let's calculate the spring potential energy. That's 1/2 kx squared. So 1/2 times 5 times 0.1 squared. That's equal to 2.5 times 10 to the minus 2, or 0.025 joules. Okay? Now, I'd like you to do one. Okay, so here's the puzzle. Suppose that I was studying a mass spring system, and I noticed that when the object attached to the spring was moved this distance from the equilibrium position, I noticed that the force, the spring force on the object, had a magnitude or a strength of this, of 30 newtons. Okay? So if I stretch the object 0.3 meters from the equilibrium position, the spring force on the object is 30 newtons. So with that information, can you tell me what the spring constant for the spring is and what the spring potential energy of the mass spring system is? Okay? So pause the video and try to work that out now, please. Okay, so I'll go ahead and work it out also. So we know that a spring force is equal to minus kx. Okay, so therefore the spring constant is equal to the F spring divided by x, and let me put an absolute value. Let me put absolute value bars here because I don't want to mess with the negative sign. So 30 divided by 0.3, so that gives 300 divided by 3, or 100 newtons per meter. Okay, now for positive x values, the spring force formula would give a negative answer. Okay, however, 30 newtons, I define that to be the magnitude. The magnitude is always positive. That's why that's not negative, if that was confusing you. And then finally, let's calculate the spring potential energy. So that's equal to 1/2 kx squared, which would be 1/2 times 100 times 0.3 squared, or 50 times 0.09. Okay, so that is equal to, let's see, 4.5 joules. I hope that's what you got.